All right. Our discussion today is on trajectory planning for robot manipulators. The content I'm going to present to you today is based on a past master's project by Chintaka Porogama and certain contents coming from not within his master's, from other sources. All right. So let's look at why we need why we need trajectory planning rather for robot manipulators. Now, here you can see a few photographs of manipulators being deployed for various industrial applications, right? So maybe welding, part handling, and automotive industry, assembly, etc., right? So all these different operations in industry where you use manipulators um, need trajectory planning, right? Think about pick and place operation that you see lower uh, down position, right? Uh, Over here, the robot manipulator has to pick up the pallet from a place, pallet feeder, and then move it to some other place, right? So it is point to point or pick and place, picking from one point, placing on another point. So when I say picking from one point, there's an orientation also, right? The pallet is on a certain orientation. And when you place it on some other place, you can't just drop it randomly, right? It has to be placed with a certain orientation. So position and orientation both are very important. I think about fixing a fixing a wall fixture something, right, using a screwdriver and a screw, right? So you need to drive it, right, in that axis, right? Then only it will move into the wall, right? The screw. So even if you get the tip of the screwdriver on the head of the screw, if you don't have the orientation, right, you can't do that. So it's not only position, orientation also. So most of the applications, right, you will see um, this orientation also a very, very important requirement. But there are some other applications where only position is important, right? Not the orientation. For example, writing on paper, right? Some people write with a vertical pen, angle pen. A lot of people use angle pen, right? So the orientation doesn't really matter there, right? As long as you have the tip of the pen on paper, that's all what you need, and bit of a pressure. There are applications in industry where you have this kind of requirement, right? You don't really need to worry about the orientation of the end effector of the manufacturer. So that's how it is in industry. Most of the industrial applications where you deploy robots for, they need position and orientation both. So look at these applications: assembling, loading and stacking, automated welding, etc. Right. So that's why we study the trajectory planning in this course. Now look at this diagram. It shows you a lot of things. You can see 4 joints of this manipulator: theta 1, theta 2, theta 3, theta 4, right? The 4 joints. And then you see the end effector over here, right? At this point, where I have my laser pointer located. And initially, maybe it was like this at this point, right? Where I have the laser pointer located now. This is the start point. This is the end point. You may say this is the peak. This is the place, pick and place. And in between, there's a certain path the manipulator takes. So our focus is what is this path? And we also call trajectory. What is the difference between the two, path and trajectory? So our discussion is on that thing, right? And you can see over here, path and trajectory. So when I say path, only the geometric description, X, Y, Z, in three-dimensional space, start point, end point, or picking point, placing point, X, Y, Z here, X, Y, Z here, right? So, and you can draw the line, and in between there can be so many of these points. They're all in X, Y, Z space. First point, end point, and all the points in between. That's the path. It's just a drawing. But when you say trajectory, time-stamped path, it is the same path, but now you have time-stamped. So every point on the way is not only the position, but the time is also stamped. The trajectory is four-dimensional, t, x, y, z, whereas the path is three-dimensional, x, y, z only. Okay, so now you understand what do I mean when I say path or when I say trajectory, all right? So finally, what really is required for a robot manipulator and its control system is not the path, but the trajectory, right? At what time should I bring the end effector to this point? At what time should I bring the end effector to that point, right? So time is important. Now, if you look at the trajectory planning process holistically, this is what you see, all the steps. So first you have a task. You are dealing with a robot manipulator for a certain application, right? Maybe pick and place, maybe laser cutting, welding, part handling. So that is the task. It can be a simple task, can be a complicated task. If it is a complicated task, you break it down into a small modular or task segments, each of which you can handle, you can plan, execute, right? The task is something you can handle. Then you have the task plan, right? So what is your plan in implementing? This is a higher level thing, right? An action plan. So what sort of action do you need to implement the task, right? It involves like, say, sometimes you need to pick up the tool also, right? And then you go to the start point and then say, scribe it, right? The engraving operation, and then to put the tool back in the tool feeder, something like that. In CNC machines, that's what we do, right? So it's not only the tool operation, but all the other things included. Once it is done, you have the path. You know the geometric path where the end effector has to move, right? Not only cutting, seaming, or whatever, painting, all the other movements. Say, for example, when not in operation, the manipulators are parked or they moved back to home position. So every manipulator has what is called home position, right? So when you start your manipulator from the home position, so there are certain other paths you have to follow to bring it from home position to the start position. Okay, right. So after that, you plan the trajectory. You put the timing on top of the path. All right. So sometimes you have, say, if you have a very short time, it's not enough for manipulator to execute, right? You have to give sufficient time for the manipulator, for the control system to implement your commands, right? And if you leave a long time, unnecessarily long time, again, that is not good because you're not using manipulators to lengthen the operation, right? But you want to shorten it, make it fast as possible, right? You want to finish the work as quickly as possible. So therefore, you want to reduce time, right, and maximize the speed again with the limits. All right. Once you have the trajectory, you send it to the controller. Okay, this is my trajectory. This is time. This is X, Y, Z. Execute it, right? Then controller does that. Robot is in the motion with all the other activities, open gripper, close gripper, move, and then release the grip. So all sorts of things, right? Uh, Specified by the task plan and action plan. So while it is doing, it also reads sensor feedback, joint encoders, and any other feedback. If it is a gripper, you want to make sure whether the gripper is closed or open, and what is the pressure like applied by the gripper, whether it is holding the object it is supposed to hold, or whether it is dropping it. All these things should be measured on the fly. So this is the entire process vertically illustrated. And if you get a path segment, right, you can see the diagram over here. You specify the path, okay, in terms of these geometric parameters, and also path constraints. You can see here path continuity, smoothness, right, and any curvatures, um, and also the time, maximum speed. All of these things, right, are specified. Usually the manipulator manufacturer's datasheet has all of these things. You just need to read from the datasheet and plan your trajectory accordingly. And if you do everything on your computer, you need all these data as data items reading from the data sheets. But if you use a state-of-the-art manipulator in today's world, right, they provide all of these things in one single package. It's like more like turnkey. You don't have to do your own programming, path planning. You just need to use the front end, the interface. It has all of its constraints, joint speeds, joint accelerations, etc. And then once you specify the key points, okay, of your motion and all the other activities like open, close, grippers, and all that, the software the manufacturer provides you can actually plan the entire trajectory. Okay, so that's how it happens in the modern world. But it's very important as engineers, you need to know how it happens, all right? Because some of these ready-made solutions might not be the most optimal solutions that you want, depending on your requirement in industry. So in that case, maybe you need to do a bit of research and tweaking the system. In that case, you definitely need to know, right, how it is happening. Probably if the code is open, enter the code and see where what is wrote, right, written, and then change the parameters to make it more appropriate, suitable for your application. So therefore, it's absolutely necessary that you know all these things, how it happens. Now, when you have the trajectory plan, what you have is from one point to another, maybe it's a series of points, right? Maybe 10, 15, 20, 30 points. And you have the trajectory, a path, X, Y, Z, and with time. Okay. So this is what the controller needs to implement that motion. Now, as you all understand, we define the manipulator applications in XYZ Cartesian space, right? Also the speeds and acceleration. We all define these things in Cartesian space, right? If you use a manipulator for welding, for example, the torch speed is in meters per second in Cartesian space. But however, again, you know that the robot does not understand the Cartesian space. It understands the joint space. Here, you can see that the robot controller can only read theta 1, theta 2, theta 3, theta 4 from the joint encoders. It cannot read the blue path here. It doesn't know that. Of course, unless you have a camera system which measures the position and communicate to the controller. And that's a separate matter. Some applications are implemented like that, direct feedback from XYZ. But the internal sensors of the joints give the controller the feedback of the joint angles, velocities, accelerations, right? All in joint space. So you can see two coordinate systems, right? X, Y, Z, X dot Y dot Z dot, X double dot Y double dot Z double dot. this position, velocity, acceleration. In the joint space, theta, theta dot, theta double dot, right? So we find it easy to define everything in XYZ space because we can perceive that space. But the manipulator, what it can perceive is theta 1, theta 2, all these joint angles and velocities, accelerations. So you need to switch back and forth between these two coordinate systems, right? So for that, we have what? The static kinematics, differential kinematics, right? To change positions and velocities back and forth. Right. So there you can see this trajectory. Once you have the trajectory, it can have either of these two forms, right? Joint trajectory form or Cartesian trajectory form. Now, what we really need to be careful about is not to exceed the joint limits. Every joint of the manipulator, you can let me go back to this one. Every joint has maximum speed, maximum acceleration. You cannot exceed those limits. So even if you plan your trajectory in X, Y, Z, I want this speed for welding, whatever, laser cutting. Once you convert it back to joint space, if the joint speed in any of these joints, right, exceed that limit, you cannot implement that trajectory. And you have to change the time, give it a little more time and reduce the acceleration. So you have to do that. So therefore, this part over here, right, you have to check thoroughly whether you are exceeding joint accelerations, joint velocities, whatever, right, before you actually use the trajectory that you developed to control the manipulator. Now, this slide takes you one step deep into the project, to the problem rather. There you can see the manipulator, and you can see the red dots here. These are the specified points for a particular application. Point A, maybe start point, C, end point, and there's another point B, the via point. Or maybe A is the start point as well as the end point. It has to come back to the same point after going through B and C. Okay, and it will go again and again and again, like that. So everybody can perceive that, okay, we will have the trajectory like that, elliptical trajectory. You can parameterize it and then get the samples at equal intervals, right? These yellow dots are those samples. So now you have not only the ABC via points, you have hundreds and if not thousands of points, okay? They're all in Cartesian space. So we call it path P, okay? So if you follow this block diagram over here, we see number one, task planning, and then number two, sequence of post points. Right? These are the knot points, A, B, and C, knot points, okay? And interpolation in Cartesian space, that is this interpolation around this path over here, right? And you have Cartesian geometric path, which is all of these points together, right? So that is the Cartesian space path. But you cannot use this one to instruct the controller to implement this motion, right? So for that, what you do is you convert path sampling and inverse kinematics, right? So you do the inverse kinematics. The moment you do that, you go from Cartesian space to joint space. Now for each point here, X, Y, Z, is 3 points here, right? One is Q1, the other one Q2, Q3. So this is just an example of a 3-link manipulator. It has 3 joints, so you have 3 angles. So these are the 3 joint positions of joint 1, joint 2, joint 3 that will position the end effector maybe one of these points, okay, A or B or any other yellow points in between. So for each sample point in Cartesian space, right, you have 3 dots here for Q1, Q2, and Q3. All right. Now this data file, you can see, you can put the time also, right, between these points. Same timing over here. So at any moment of time, you know what is Q1, what is Q2, what is Q3. So you give these as reference points to the controller. So the controller will try to move a joint 1 to Q1 position, joint 2 to Q2 position, joint 3 to Q3 position, right? And each timestamp, the controller will make sure that it drives the 3 joints to their respective positions. So when you do that, the endpoint will be located in the corresponding yellow point, yellow or red point. So this is what happens in manipulator controls. Now I think it's time to look at, compare a little bit deep into the joint space and operational space planning, right? Now, joint space description. Entire path is described or presented in terms of joint angles, okay? So therefore, the motion between the 2 points is unpredictable. So what do you mean by unpredictable? Because all these points are known, right? So this, what we really mean by this unpredictable nature is that even though you take 2 points in Cartesian space, point 1, point 2, and you convert these 2 points into joint angles, right? Q1, Q2, Q3, and final point Q1, Q2, Q3. And then you sample between the 2 points and execute. So when you execute that, the end effector will not go in a straight line in the Cartesian space. When you see how the robot is moving, it will not move from point A to point B on a straight line as you see it, because the trajectory is planned in the joint space. You have maybe linear sampling in joint 1, linear sampling in joint 2. But you know, if you look at the forward kinematics equations, they are not linear. They are highly nonlinear, sines and cosines and stuff like that. So therefore, even though the joint trajectory is linear, when it is transformed into Cartesian trajectory, it's not linear. It's not a straight line and go in a certain curvature. So is that what you want? That's something the user has to decide, okay? Do I really need a straight line in Cartesian space or not? Meaning, as long as I can position the manipulator at the start point correctly and at the end point correctly. That if that is all what I am really concerned about, not the path it takes in between, then I would say that's fine, right? Even though the end effector goes through whatever curvature, right? It's all right because I don't really care about the path it takes as long as it finally goes to the end point, all right? In that case, you can plan the entire trajectory in joint space. So easy. You have only few points in Cartesian space, do the inverse kinematics and get the joint angles, and after that, plan the sampling entirely in the joint space. It's so easy. But however, if you are dealing with, say, welding operation, right, there you are. Welding is point to point in close proximity defined in Cartesian space. It's not only the first point and the end point, right? When you weld, you have to weld on that line, straight line or otherwise, whatever that curvature may be, you need to weld it that way. So unfortunately, you can't have joint space trajectory planning. I just explained earlier for that kind of applications, right? Okay. For that, you need to have operational space description. So entire trajectory, right, point to point, very close proximity should be defined in Cartesian space. The motion between the 2 points is known at all times. Visually, you can present it, right? This is where the end effect is going actually, right? Now, after that, you convert that into joint space. There are thousands of points in Cartesian space, and each point is converted to joint space, right? So this is in contrast to what we earlier explained, in which only the few via points are transformed to joint space initially. And then using these few points in joint space, you interpolate and generate the entire trajectory. Okay. Here it is not the case. Operational space description, you have to generate all the points in Cartesian space. And then each and every point, all the sampling, interpolation, everything happens in Cartesian space. And then each and every point is inversely transformed to joint space. Okay. Advantage is it's very easy to visualize the trajectory, end effector trajectory, where it is going, whether it is going to hit somewhere else. All these things can be visualized before you implement. The disadvantage is computationally not very efficient because there's so many inverse kinematics happening, right? So it costs a lot of computational capacity. The first one, joint space description, is computationally very efficient because the interpolation happens in joint space. You don't have inverse kinematics involved to a greater deal there. But the disadvantage is that there's a bit of a risk of where the end effect is going before it goes to the next point. The path it takes in Cartesian space is not predictable. That's what I said, unpredictable. Of course, if you do that offline and visualize, you know where it is going. This is what we do. So this unpredictable word is a bit exaggerating in that sense, but I use it to give you the message. Now, this is what happens if you do your planning in operational space or Cartesian space. You can see 3 photographs here, right? They're all from Craig's book, I think, J.J. Craig's book. You can see this one. End effector starts from point A and goes to point B on a straight line, like welding, laser cutting, etc. This is what we do. You can see small calibrations here. These are the sample points. They are all in Cartesian space. So in actual motion, you need to inversely transform each and every point over here to the joint space. Right? Now look at the second one over here. Point A, start point, point B, end point. Right? And if you do the joint space planning, right? Or rather Cartesian space planning in the first place, right? You can have point A, point B, they are all both feasible. Now you do the sampling in between, right? Not knowing that it is not possible to go through itself, right? This is another danger in Cartesian space planning, right? Even though point A and point B are both accessible, there can be a little danger that you are planning your trajectory so that the robot goes through itself. It is obviously not possible. And if you try to implement this, if the software has all these checks, it will not allow you to operate it. If it doesn't have that kind of fail-safe or safety precautions in the software, you will feel it, experience it in operation, robot goes to that limit somewhere here and hit the limits and stop. Okay. So these are some of the problems in Cartesian space planning also, right? And look at this one. The robot moves from, let's say, from here to here. That's fine, right? This is the start point. I think I should have taken A from, to here, B to that point. What do you think? Your first point is feasible. Your last point is also feasible. There are a lot of points which are feasible, right? Except these 2 points in between. Because to go for the robot arm to go from here to here is a very small distance in Cartesian space, and you think, okay, this is a small distance, but in fact, depending on the kinematic structure of the manipulator, it has to change from left side to right side, right? To cross from A to B, as you see over here. It's a huge motion of one of these joints to bring it from left-hand side to right-hand side, as you see. So this is because of the structure of the manipulator, how the links are connected and all. So therefore, you have to be a little careful when you plan your trajectory entirely in Cartesian space, because even though it is a very small distance in Cartesian space, it could go through a singularity point, so that one of the joints will have to drive a huge amount, which is not actually visible in the Cartesian space in terms of the end effector motion. So these are practical scenarios you need to keep an eye on, right? Planning your trajectory in Cartesian space. So the good thing is that you can visualize it. You can visualize it before you actually use your trajectory that you have planned to control the manipulator. All these things can be visualized and figure out, oh my God, there's this point. This trajectory is not working because it's going like that. Okay, right. So once you're cleared with all of these troubles in the Cartesian space, robot doesn't go through itself, or it doesn't have to change from left to right configuration. Your motion is smooth and nice, and you know exactly where end effect is going in Cartesian space. Then you can transform that to the joint space easily. Any questions? Is everything clear up to now?
So is there any particular reason why we are using these two spaces, say, operational space and joint space, like any instances where we actually differentiate this when you're planning?
Uh, well, there's no preference. There's no preference, and depending on the application, you have to go for the most appropriate one. All what I explain is the advantages and disadvantages of planning the trajectory in these two spaces. Of course, there's no other space, Cartesian or joint. If I summarize again briefly, if you look at an application, let's say welding. In welding, you have to move the end effector in Cartesian space from a point to another point, say through a straight line, right? There are welding happening in not in straight lines, but curvatures, but not to invite additional problems, let's say straight line welding. You have seen straight line welding most of the time, right? So it's a straight line in Cartesian space by nature. You have to move the end effector through that straight line. So you have to plan. There's no choice here, right? You have to plan your trajectory in Cartesian space from XYZ of A to XYZ of B, and all the XYZ in between. It's a straight line. But the thing is, A robot doesn't know X, Y, Z. Robot knows the joint angles. Right? What is this angle? What is this angle? What is this angle? These angles. So when at point A, what are these three angles? So you have to calculate these three angles using inverse kinematics. And when you have these three angles, you are in joint space. Then you can instruct, you mean the controller can hold the joint 1, 2, 3 into their respective angles. Because control system is basically joint control system. There are motors here, here, and here. You control these motors, right? They are DC servos most of the time to move into that angles, angle 1, angle 2, angle 3. That's how you hold your start point A. This is a welding torch. You hold it at this point. When it comes to controls, it's joint space. Robot joint controllers can maintain the joint position and control the joint position, right, according to a planned trajectory. It cannot do anything, right, in the Cartesian space, unfortunately. The joints are actually connected with the motors and encoders. So feedback is from joint encoders. Control is on the position side, right, using PWM. So on the other hand, if it is not a welding kind of application, if it is a pick and place application, you pick from this point, place from the other point. Anyway, you have to move from here to here, but you don't have to move along a straight line. There's no such requirement. And you can move it through any curvature. You just need to go to the endpoint and place it. So we call these motions point-to-point operation. In that case, you don't have to have this straight line or whatever in Cartesian space and sample it, right? And each sample transform inversely to the joint space. You don't have to do any of these calculations. All what you need to do is first point, last point. That's it. First point, use the inverse kinematics, go to the joint space. Last point, use inverse kinematics, go to the joint space. Now you have 2 points in joint space. You interpolate, right? Joint 1 from this angle to that angle. Joint 2 from this angle to that angle. Like that. Then you generate all of these intermediate points in joint space, not in Cartesian space. So with this knowledge, you have to customize it to your application. That's all what I have said. No, there's no preference to select this or that. It depends on the nature of the application. Based on that, you have to find out the best or optimal trajectory planning, whether it is Cartesian space or joint space or a combination. Is that clear?
Yes, it's clear.
All right. Any other questions, please? All right, let's move on. Planning in operational space, XYZ, I have already explained. Just go through the summary again. Calculate path from the initial point to the final point. So welding is the basic example, right? Everybody knows about welding. Is Cartesian space, operational space planning. And you assign a time, right, from start to end. What is the total time? And then discretize the points. So you can see we are actually doing this one, right? Blend a continuous time function between these points. Solve inverse kinematics at each step. So every step of the way, this calibration, you have to do the inverse kinematics. So inverse kinematics is difficult to solve sometimes. You have to have numerical techniques. Say, for example, Newton-Raphson method, right? It's not a like closed form solution, right? So you have to do it iteratively. So it takes time, right, to get to the solution. So that's why we don't like to solve inverse kinematics very often, right? In robot manipulators, because it takes time. You need very expensive, fast computational platforms to solve inverse kinematics in real time. But the advantages are collision-free path can be obtained. So all these things can be visualized and eliminated, right? So if you really want to go from A to B, of course, you can't go through a straight line. Why don't you have another point somewhere here? Say C. So you go from A to C and then C to B. So you can visualize and implement, introduce modifications to the path so that these collisions are not possible. Okay. Here also you can visualize there's certainly a problem and do something about it, right? All these things are possible in Cartesian space. The disadvantages are computationally expensive, having to deal with inverse kinematics, having to solve inverse kinematics on the fly in real time is a huge computational burden. And it is unknown how to set the total time. Yeah. So it's not perfectly true. You can have a software to tell you the optimum time straight away once you specify the path. So if you have to specify the time upfront in priori, it's a problem. But you can have the system develop in such a way so that it will automatically set the optimum time, right? In that case, you get rid of this disadvantage also, how to set the optimum time from A to B. But if you plan in joint space, calculate inverse kinematics from initial point to the final point, right? Uh, Initial point and final point, not from, I will adjust that one, right? Inverse kinematics solution at initial point and at final point, only that, not in between. Assign total time using maximal velocity in joints, then discretize the individual joint trajectories in time, blend a continuous function between these points. So everything is happening in joint space. You can set the time very easily because you know what is the first joint angle, right? At the initial position was the joint angle 1, and at the final position was the joint angle 1. This is joint 1, okay? Angle 1 and final angle. So you see the difference and you know what is the maximum speed for that joint. So divide the total angle by the maximum speed, you get the time, minimum time. So very easy to set the time and all that, right? So do it for the second joint, third joint, fourth joint, you get minimum times, right? So out of that, you get the maximum, minimum time, max mean. So then you are fine, okay? Yeah. Advantages, inverse kinematics is computed only once, right? Once or twice, initial point, end point, only that. Can easily take into account joint angle velocity constraints. As I said, you set the joint angle limit velocity, right? Or maximum acceleration, whatever you can put that and plan the trajectory in the joint space. But there are disadvantages also, that is cannot deal with operational space obstacles. So as I said, and the end effector is moving not in a straight line, right? It's some awkward trajectory from start to end point. It might hit something in the vicinity, and unless you simulate and see using forward kinematics where the end effector is moving, right? You don't know where it is actually moving, right? So that disadvantage is there. All right. So then let's look at different types of motion. The most typical one is point-to-point motion. End effector moves from start point to end point in the workspace. This is the start point, end point. That's it. How it goes, what path it takes in Cartesian space, our space, is not a concern at all, right? It can take any path. We don't care. But here is the start point and end point. So all joints movements are coordinated for the point-to-point motion. End effector travels in an arbitrary path. That's this path, okay? Not a straight line. Okay. And motion with a wire point. This is start point, end point again, but the manipulator has to go through another point in between. So then the path planning is a bit different, even though it looks like repetition of the first thing, point to point. So point to point here, then point to point here. But the problem is when I say point to point, I usually assume that the speeds are zero. Speeds and acceleration are zero here. You start with zero speed, zero acceleration. You end with zero speed, zero acceleration. But when you have wire point, it's not the case. You don't stop at the wire point. If you stop at the wire point, yes, then it is repetition of the first problem. But if you don't want to stop at the wire point, right, it is stitching of two segments. So then trajectory planning is a bit more complicated. Now, this is the entry point for the core discussion today. When you have a wire point, right, how do you make sure, how do you plan your trajectory so that it goes from start to end through the wire point without stopping at the wire point? Okay. Right. So now let's take joint space planning and dig down a little bit. Now you can see over here, the manipulator, right, with three joints, theta 1, theta 2, and theta 3. This is the start point in blue color. That is A, and this is the end point in green, theta 1, theta 2, theta 3, right? So you can see the joint angles, theta 1A, theta 2A, theta 3A. This is for point A. And theta 1B, theta 2B, theta 3B, this is the joint angles for point B. In between, the path is arbitrary. How do we plan the path? It's as shown here. You can see at the start point, theta 1A is over here. This is theta 2A. This is theta 3A. Okay. When you start your motion, these are the positions of the angles, right? The joints. After a certain time, when the end effector moves to the end point, you have joint 1, right, with this angle, theta 1B, and joint 2 is at theta 2B, and joint 3 is at theta 3B. Now, forget about the curvature in between, right? You have first point and the second point for joint 1, first point and second point for joint 2, first point, second point, joint 3. Now, it's all up to you to set a trajectory in between. And if you want to go straight line, it's a linear interpolation from here to here, from here to here, from here to here. Not what I have shown here, right? The curvatures. You can go for a straight line. It's so simple. But if you think in a slightly different way, right? Linear interpolation is not good. If you want to have more smoother motion, you can fit any curve. right? For joint 1, joint 2, joint 3. It can be a polynomial, right? It can be a parabolic path, can be anything, exponential or hyperbolic tangent function, you name it. You can fit any graph, any trajectory between A and B. All what you need to do is to assure that you connect these 2 points through any curvature. Okay. So number 3, step 3 is interpolation of start and end point, theta 1a to theta 1b. What is the curvature? Theta 1t, theta 2t, theta 3t. So 3 joints have 3 profiles. Right? How to fit the trajectory, we'll discuss little later, but this is the process. So this allows you to have smooth motion. If you are, depending on the trajectory you fit over here, right, you can make sure the joints are moving very smoothly. Okay. So the purpose of planning the trajectory is make sure it is actually the optimum path planning, which includes a few things. Number 1, it is fast. Okay. Generally, we need speed, right? Number 2, it doesn't have a lot of vibrations, doesn't cause unsmoothness in the trajectory, right? You need to have smooth operation. Smooth doesn't mean slow, right? You can have fast motion, yet it is smooth, right? So considering all these things, you can plan the trajectory. So entirely in joint space. Now, suppose you generate a very smooth trajectory, then you enjoy these benefits. But if you don't have a smooth trajectory, what will happen? Your trajectory is not very smooth. It's a non-smooth trajectory. So you will see vibrations. When the robot is moving, you can hear this screaming sound, and also sometimes you can feel the vibration, right? The table on which the robot is actually located can also vibrate, making sound and all that. You will hear all these things. And if the motion is very smooth, sometimes you don't hear anything. You can see the robot moving, but it doesn't make any sound other than this powering the motors, and motor motion generate a little sound, only that. Okay. And also, if your path is very smooth, actuators do not saturate. They don't go to the maximum limit and hit the ceiling and stop. It doesn't happen, right? So therefore, any path deviation because of actuator saturation will not be there. But for whatever reason, if your trajectory is not smooth and optimal, if it drives one of these joints to its limit, hit the limit, let's say if we talk about PWM conditions, it hits the 100% PWM and needs more. But unfortunately, the motor cannot be driven more than 100%. So it runs at 100%. And then you will see the deviation of the end effector, right? It's not going along the planned trajectory, it deviates. So uh, that will create poor quality in whatever work you are doing. If it is a laser cutting, for example, you want to cut a curve, and all of a sudden in the middle, it goes out of that curvature, right? So probably that is not acceptable. So these things can happen if you do not plan your trajectory, right, accordingly. That will also lead to shortening the manipulator lifetime. So when uh, you are actually hacking the manipulator, if you have a very non-smooth trajectory, which makes the robot vibrate and all that during operation, it will lose its um, quality and integrity in the joints and all that will cause loosening of these joints and couplings and all that. So lifetime will be affected. So that's why trajectory planning is very, very smooth. Okay. So you need to have that in your trajectory planning algorithm. Make sure your trajectory is the optimal one and it is fastest, and it also gives the smooth operation. Right. So that is the first part of the lecture. And the second part, we start from here. I'm going to show you different techniques that you can actually design a path. Okay. So before I take this over, let's take a little break, about 5 to 10 minutes. Let's look at the first trajectory planning algorithm, that is uniform velocity trajectory in joint space. All right. Now here you see uh, the joint moving from one angle to another angle, right? From QS to QG. So if you know the difference, QG minus QS, and also the given time, TG, you can calculate the velocity, uniform velocity. This is the velocity you have to travel from start to end. And if you put that into the first equation over here, you can calculate the joint angle at any time t, which is equal to start angle plus velocity times time. Pretty straightforward, okay? And now, if you plan your trajectory this way, the problem you are having is that at the start point, you suddenly get a velocity from zero. And also at the end point, you reduce the velocity from q dot t to zero, okay, suddenly, causing huge accelerations. So that is the problem of this very simple trajectory planning algorithm. So we do not encourage to have sudden accelerations in the trajectory. Do not plan your joint trajectories with sudden acceleration. It is not good. Okay. Right. So we'll have to see other trajectory planning algorithms. The second one is triangular velocity trajectory. Okay. Not a flat velocity. Now it is a triangular velocity trajectory. You can see it over here. Q dot T, the velocity is like a triangle now. So the first part, you have a positive acceleration. The second part, you have a negative acceleration. By magnitude, they are equal. And your actual angle would look like an S curve here, right? S curve here. This is a kind of parabolic shape, and there's another parabolic shape and combined together, right? So what are the equations here? Well, we can write down the equation for the total angle traveled, right? And total angle is equal to the area of the triangle. And I can write down this equation. QG minus QH is the total angle, is equal to half of the base of the triangle, that is half of TG times the height. Height is again half of the base times tan theta. Tan theta here is actually acceleration. So Q double dot minimum times TG by 2. This is the height. This is half of the base. So from this equation, you can calculate your acceleration, Q double dot minimum, right? So why I call it minimum is that this is the unique triangle that will give you the area under the triangle, which is equal to the total angle that you have to travel, okay? If you have a high acceleration, this triangle will be taller and you will drive the joint more than what you're supposed to drive. If it is a 90-degree motion, you are driving more than that, 100 degrees. And if you reduce the height or reduce the acceleration, then it's a smaller triangle. Again, you don't have the same angular displacement. Say you are supposed to drive by 90 degrees. Now you are actually driving 80 degrees. Not enough. So this triangle is unique to the angle you have to travel. That is QG minus QS. Okay. There's a unique triangle. Therefore, there's a unique QW. Okay. It's a unique one. To emphasize that you cannot lower the acceleration below this point, I put this minimum subscript. And Q double dot minimum has a positive sign if it is acceleration in the first half, negative sign if it is a deceleration in the second half, right? Like that. Now, if you know the acceleration and the deceleration, right, the second half, you can put that into the equation of motion, right? S equals ut plus half at square, initial velocity and acceleration. You can get these two equations for the first half, for the second half. Pretty easy. Now, what is the problem? Again, here you have acceleration discontinuities at the end points, first point and the second point. Okay, you can see it over here. Acceleration has a certain value and it's constant for the first half. And then you have a deceleration, constant for the second half. And they suddenly drop to zero at the start and at the end. So this is the problem. So we need to have trajectory planning algorithms that give us smooth velocity. We talk about smoothness of the trajectories all this long, right? To get smooth trajectories, we need to have continuous velocity, continuous acceleration profiles, right? If you start with zero velocity, zero acceleration, your trajectory planning algorithm also has to start with zero velocity, zero acceleration, right? Otherwise, it will create a jerk. The moment you start, it starts with a jerk, which is not good, okay? Right. Let's look at the third trajectory planning algorithm, right? This time it is trapezoidal. So now please track all these things, right? First one we discussed was uniform velocity. Second one, triangular velocity. Now it's a trapezoidal velocity profile. We keep improving the quality of the trajectory. Now here you can see, let's look at the velocity trajectory first, right? You start with zero velocity and accelerate to a certain velocity. And then you maintain that velocity for the most part of the motion, and then you decelerate and stop. Can you see that? You start with zero velocity, you end at zero velocity. And the middle, there's a bigger portion where you travel with uniform velocity. Okay, so you assure the velocity continuity here, right? And if you convert that into acceleration, you can see, well, acceleration is not continuous at the start point. There's a high acceleration for a certain period of time, and then zero acceleration. This is good. Zero acceleration is good. And then the deceleration, and there's a discontinuity again. All right. So acceleration discontinuities happen here, 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 and here. Sometimes acceleration discontinuities are okay. So there are a lot of industrial manipulators that they only concern about velocity continuity, right? No discontinuity in velocity. Of course, in acceleration, they don't care, right? But advanced trajectory planning algorithms, they try to bring some sort of continuity to the of the acceleration to the trajectory planning algorithm. Now, if you look at what's happening in the angle, it has the S curve now, but with a linear portion in the middle. Earlier, it was like S curve from here to here, right along. It was a S curve like that, okay, with the triangular velocity profile. But with the trapezoidal part, you have the linear part in the middle. So now it's a straight line from here to here. That's the only difference between this one and the previous one. So these are the blend points, blending. You have this uniform acceleration part. Here is another uniform acceleration part. The parabolic curves in position. And then you have the uniform velocity or zero acceleration in the middle part, the linear portion. These are the blend points here, 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 as well as here. So acceleration discontinuity at blend points. This is the downside of this trajectory planning algorithm. But keep that in mind. This is one of the famous trajectory planning algorithms, the trapezoidal one. Initially, there's a discontinuity, but once you get through that, 80%, 90% of the motion is very smooth, like that, the middle part. You want to make the middle part as big, as long as possible. And initially, at the start point and at the end, there's some sort of discontinuity. And it's not part of the operation. Maybe it is welding, seaming, cutting, whatever. Is not part of this final point here and here. Entire trajectory is actually operation happens over here, right? Where you have smooth motion. So let us continue with the trapezoidal velocity trajectory for a while. Then let's try to write down these equations, right? The first equation we can write is the total angular motion from start to the end, the total angle. As you can see over here, it's two triangles and one rectangle in the middle, right? The total area under the velocity curve is the angle here. So you can write down this equation. Please follow it carefully. Qg minus Q, sorry, this is Qs. It has to be Qs. The total angle, right? 2 times half of the base here, that is half TB, times the height. Height is Q double dot B, that is the acceleration, times TB, okay? Right, height. Plus the rectangular portion here, that is Q double dot B times TB, that is the height again, times the distance. This is the time actually. So it is Tg minus 2Tb. So Tb is this time. You get rid of 2 of these from the total time. So this is a rectangular part. This is the triangular part, okay? 2 of them. So then you can simplify this one into this equation, which gives you, can you see that Tb square and Tb square here? So it's a quadratic equation of Tb. Quadratic equation of Tb, right? So this is that quadratic equation of Tb. So where you want to stop your acceleration, okay? How far you want to maintain this acceleration, right? So depending on that, you have a series of solutions, right? Now, if you solve this quadratic equation, you get it like that. Tb, this one, is equal to Tg by 2. That is the half point. Total time is Tg. Tg by 2 is right in the middle, right? Then plus or minus. You get the two solutions, right? half of square root tg square minus this whole thing, coming from the quadratic equations, right? Nothing new. So this equation is actually reassuring of what you see over here. Of course, we know TB is half of TG plus some quantity minus the same quantity, okay? 2 points. Now, now think about the acceleration. If it is a variable, you have many solutions, right? What if you reduce the acceleration? When you reduce the acceleration, what happens is that if you reduce the acceleration, it will go like that, little bit further, and then maintain the uniform speed, and then decelerate and stop over here, something like that. So then TB would be over here and over here. Can you see that? When you reduce your acceleration, your middle portion will get squeezed, okay? And there is a point where, right, you turn into triangular shape like that, triangular shape, right? Then absolutely no middle part. This is the triangular velocity profile we discussed earlier. Now, the plus point of the trapezoidal velocity profile is that you have a long central linear portion, which gives you very smooth motion, right? It can be painting, it can be welding, laser cutting, whatever. If you can maintain this uniform speed, right, you assure quality of work, right? And remember, this is joint angle, not the Cartesian trajectory. This is a joint trajectory, okay? So for a linear portion to exist, right, for this linear portion to exist, the acceleration has to be, well, this second part over here, right? If you get TG right over here, you add a little amount and you subtract the same amount. That amount has to be greater than or equal to 0. So that is the quantity within the square root over here, right, has to be greater than or equal to 0, which means acceleration has to be greater than or equal to this one. This is the same equation we received earlier, minimum joint acceleration, okay? You cannot reduce the acceleration below this value, q double dot b, right? Now, if you have many points, and if you want to apply the trapezoidal trajectory, right, for a set of points, not 2, maybe 3, 4, 5, like that, what you would be doing is just this. So you take 2 points and plan the trajectory, and then at another point, plan that trajectory segment and go on, right? So this is what is called multi-stage linear parabolic blend or spline, okay? Trajectories are planned separately, but then connected together. So you have the same equations as we discussed over here, but you have to apply for this set of equations, right, for the first segment, the second segment, third segment, and so on. So when you do that, whatever initial velocities you have to consider for the final velocities that you end up in a segment should be the initial velocity of the next segment, right? Otherwise, there's a discontinuity. Or else you have, if you can assume that after the first segment, it goes to 0 velocity, so much the better. And the next segment start with 0 velocity. So you can have so many of these things and added together. That's also possible. But generally, it's not the case, right? At wire points, you do not stop. You keep going. So in that case, you have to plan it like that. Right? This is the first point. This is the second point. This is the third point, fourth point, like that. And you plan your trajectory like that. Okay. So, in fact, these points here, the black dots, are actually not the trajectory points. Okay. These are virtual or pseudo wire points. Actual point is over here, where I have the laser pointer. This is the actual point. Okay. And for this one, this is the actual point, right? These are pseudo points. We use the pseudo point to make this a straight line segment to plan the trajectory. That's all. To plan the trajectory, to segment it, right? First segment, second, third, fourth, and so on. But when you plan the trajectory, we plan it from here to here. So we are actually going through the joint angles, right? That we really need the end effector to move through, right? I mean, the joint angle to move through. So these virtual and pseudo wire points open up a new discussion. It's based on some research done in the past. Because of the blending, the straight line segment, say you can see it from here to here, is a straight line, okay? And after that is a parabolic blend to the straight line. So when you make the parabolic blend, right, it goes through an acceleration or deceleration, and the velocity changes, and you want to connect that velocity to the next segment, right? Start with the initial velocity. Acceleration, of course, there's a discontinuity. You cannot achieve all these things in a set of equations, because you have limited number of equations. You can satisfy only so many constraints, okay? You cannot satisfy all the constraints. All right. So we call this splines, which is parabolic blends, okay? When you have piecewise curves separately planned and added together, it's a spline. Now let me show you the polynomial trajectories, okay? So what is a polynomial equation? Polynomial equation looks like this. You can see it over here. The joint angle Q of t is equal to a0 plus a1t plus a2t square plus a3t to the 3. This is a third order polynomial. You can have any order. You can add another term here plus a4t to the 4. Then it's a fourth order polynomial like that. But we prefer to have as low order polynomial as possible. So let's start with cubic polynomial. Then once you differentiate the cubic polynomial, it becomes a quadratic polynomial, second order polynomial, right? Like this. And if you further differentiate it, you get the acceleration of the joint, right? It's a first order. We can't say first order polynomial, right? It's a straight line, in other words, like that. And if you further differentiate it, it becomes a constant. Okay. Now you can see it over here. This is the cubic polynomial for the joint angle, right? You start with, say, 0 and end up at 80. So this is 80-degree motion using through a cubic polynomial. So at any point over here, this is 1 second actually. In 1 second, you travel 80 degrees. Okay. So at any point, you can calculate the value using this equation. If you know A0, A1, A2, A3. The problem here is that how to find out these four coefficients. And the velocity, it becomes a quadratic or parabolic. So it's a parabolic curve like that. Okay. The velocity is not constant. It's parabolic. Now you can see the difference between the polynomial trajectories and the triangular trajectories, the trapezoidal trajectories, uniform velocities, all these things, right? You can compare and see. Now here you don't get uniform velocity, right? The velocity is like that. But you start with 0, end with 0, right? So there's no discontinuity. And what about the acceleration? It looks like this. It's also not flat. It's linear. You start with some positive high value and end up at negative high value. So you have the sorry, the discontinuity at the end points, right? But there's no discontinuity in the middle. Once you start going, acceleration is very smooth, right? I don't want to talk about jerk. It's the rate of change of acceleration. So it's a constant. You have a constant jerk. So if this is what you want, you can go ahead and plan a trajectory, right? Uh, for a joint. So all of the joints, they will have polynomial trajectories, especially here, cubic polynomial trajectories. So as you can see, we have position, velocity, acceleration. So therefore, cubic polynomial is kind of matching. Okay. Now let's see the details of how you plan a trajectory. Cubic polynomial trajectory. So let me get the first one, D1. So this is the fourth trajectory planning algorithm. And the fourth one has different forms. So I first take D1, the first variant of the cubic polynomial trajectory. Okay. So suppose you have you take one joint and you have to move it from one angle to another angle. Okay, one segment. So if you use the joint position equation number one. Okay, equation number one. Set time equals 0. So time 0 means initial position, right? So then this term, and this term, all of these three terms will vanish because it is time 0. And on the left-hand side is the position at start point, right? Initial joint angle. Because you are given this angle, you want to move from, let's say, 10 degrees to 100 degrees. So 10 is the Q0, 100 is Q capital T, that is the time given, right, for the trajectory planning. So you can write this one. QS is the start angle and it is equal to A0 because all of these three terms vanish. And if you set time to the end point after the motion, right, the time is capital T. So you can write down this equation with QG on the left-hand side. The final angle is equal to this equation, equation 5. Let's talk about speed. Joint velocity. Look at this equation, number 2 over here, right? Set time equals 0. So these two guys vanish. What is the initial velocity? That is equal to A1. So A1 is equal to initial velocity, Q dot S. What was the final velocity? use the velocity equation, substitute for simple T, capital T, right? Total time. And then you get this equation. So you have the position polynomial, velocity polynomial. You substitute initial and final position, initial and final velocity. You get these four equations, 4, 5, 6, and 7. Clear? So out of these four equations, you already know A0, the first coefficient of the polynomial, is simply the initial angle. And the second coefficient of the polynomial, that is A1, is equal to the initial velocity. So all what you need here is initial position and initial velocity. The moment you know these two things, A0 and A1 are known. So this is a cubic polynomial with four coefficients, A0, A1, A2, A3. Once you know the initial position and initial velocity, you know two of them. Then what remains to be solved is A2 and A3. Okay? So we can solve that later, but in the meantime, let's go ahead with the acceleration. What about now, hold on a second. Now, if you look at these four equations, so there are four unknowns, right? Once you substitute A0, okay, QS for A0 and Q dot S for A1, right? You can write down this equation number 5 and equation number 7 into two variable equations where only A2 and A3 are not known, okay? And you have two equations, two unknowns, you can solve it, okay? Or in other words, four equations and four unknowns. You can solve it. Once you solve A0, A1, A2, A3, the polynomial is done. It's not a symbolic polynomial. It's known. It's numerically known polynomial, and you can substitute for any t during that operation, and it will give you the position and the velocity and the acceleration. Polynomial is known. That's why. So polynomials are great things because the same equation can be differentiated to get the velocity acceleration in a successive manner, and the order reduces as you go. That's why polynomials are really, really nice, elegant formations, right? So once you solve with the initial velocity, initial and final, let's say boundary conditions for velocity and so for position and velocity, you are remaining with acceleration equation, right? If you look at the acceleration here, 2a2 plus 6a3t. Now, all of the coefficients, all four coefficients of the polynomial have already been solved. And as I said a while ago, it's a known polynomial now. A0, A1, A2, A3, they are all known. We only spend initial velocity or boundary conditions for position and velocity. Just that. Okay. And then the acceleration equation, you have to submit t equals 0, initial acceleration. T equals capital T, final acceleration. Right? So your acceleration will be like this in equation 8 and 9. These are unadjustable. You cannot adjust it. You cannot say, no, I want to have this initial acceleration. I want to have this initial final acceleration. No, you can't. Because this is only four coefficient problem, and we have already solved four coefficients using initial position, initial velocity. Right? There's no room to adjust it for initial acceleration or final acceleration. Instead, what you would do is that just calculate, okay, what is the initial acceleration then? 2a2. Is that okay? Then go ahead. If it is not okay, you have to do something about it. And the final acceleration is also the same. 2a2 plus 6a, 3 capital T. Once you calculate, you can agree or not. If you do not agree, all what you need to do is to change this capital T, give it more time and see whether it will make the accelerations acceptable. Is that clear about polynomial trajectories? Any questions, please? Bhanuka, is that clear to you?
Yes, it's clear.
Then Chamira,
Yes, sir. It's clear, sir.
Sandruan,
Yes, sir.
Darshana?
Yes.
All right. So this is not very difficult, right? This is easy. But what might be little bit not very clear is that how to put things together, right? So this is the fourth trajectory planning algorithm. Fourth one. So first one, second one, third one, fourth one. Right? Do not mix all these things, right? Make sure you know each and every trajectory planning algorithm and you know how to use it. All right. Now, what is the problem with the cubic polynomial trajectories then? Can somebody answer? What is the downside of the cubic polynomial trajectories when you want to fit it? Can you satisfy the position boundary conditions? Yes or no? Any answer, please?
No.
Initial position and final position. Can you satisfy these boundary conditions using cubic polynomials? Can you satisfy initial and final velocity conditions using cubic polynomials? Can you satisfy initial and final acceleration conditions using cubic polynomials? So 3 questions. Can you use cubic polynomials to satisfy initial and final position, initial and final velocity, initial and final acceleration? Can you do that?
Acceleration you can't.
All right. What about position and velocity?
Position we can. Right?
Position we can. What about velocity?
Velocity also we can.
Yeah, velocity too is possible. Yeah. Can you explain why we cannot have acceleration satisfied? Direct answer, please. Why we cannot use cubic polynomials to satisfy accelerations? Okay. Let me explain it again. Cubic polynomial has how many parameters? How many unknowns? How many adjustable coefficients?
4.
4. You have 4 adjustable coefficients. You adjust these coefficients in order to satisfy the boundary conditions. Each boundary condition, when you try to satisfy the boundary conditions, you set the value for these parameters. You have 4 parameters. You can satisfy 4 conditions. Once you satisfy one condition, one of these parameters become fixed. It's not a adjustable parameter anymore. When you satisfy a second condition, second parameter is also fixed, not constant. Likewise, as you satisfy certain conditions, boundary conditions, you lose your remaining parameters one by one. And after you satisfy 4 conditions, you are left with no more parameters to adjust, so that you cannot satisfy any other condition. Is that clear?
Yes.
It is not robotics problem, it is mathematics, just mathematics. Okay. If you have 4 parameters adjustable, you can satisfy 4 conditions. Now, if you look at position, velocity, acceleration, right? 2 points. You have position, velocity, acceleration here, position, velocity, acceleration here. How many boundary conditions are there? How many boundary conditions are there? You know it?
6.
6. Position, velocity, acceleration at the start point, position, velocity, acceleration at the end point. Altogether 6. You can satisfy any 4 of the 6, and other 2 you cannot. Other 2 you cannot. So it's just that. So what we do is we want to definitely satisfy the position, okay? Then velocity, if possible, acceleration. So that is the order, right? We have done it over here. We tried velocity and position, and we are done. Acceleration, we have to look at what the numbers are for acceleration at the start and the end, and accept or go back to the start point, change the time, give it more time, and work it out again, and check again what is the acceleration now, start point, end point. If it is too high of an acceleration, you cannot proceed. You have to give more time in iterative manner until you get the acceleration down to a certain level. Okay? Right. So that's about the cubic polynomials. Now let me work it out for a specific case where your initial right. So if you want to calculate, if you want to proceed these 4 equations, right? Initial and final position, initial and final velocity, right? You get 4 equations, right? How to solve these 4 equations is you substitute from 4 and 6, right? 4 and 6 to 5 and 7. Okay. So when you do that, 4, 6 to 5, 4, 6 to 7, you get these equations. And then you can work out A2 and A3 like that. Very simple. A3 and A2. And earlier, you have got straight away A0 and A1. So all the parameters are known. Now, if you set your initial velocity to 0 and final velocity also to 0, what will happen? Right? Cubic polynomial with 0 speed at endpoints. If this is the case, say for example, pick and place. You pick it from here, and when you are picking, you have 0 speed, right? And when you are placing, again you have 0 speed. So if that is your requirement, your initial and final velocities are 0. So which means you can see over here this q dot s, qg dot, q s dot. These are all zeros. Okay. Initial velocity, final velocity, they are all zeros. The dots are gone. When the dots are gone, your A2 and A3 would be like this. So therefore, depending on your trajectory requirement, these coefficients change, all right? In that case, if you look at the position, velocity, acceleration, it will look like this. Can you see it over here? Velocity, look at the velocity curve, this dash line. You start with 0 velocity, end up at 0 velocity, okay? And then your acceleration goes like that. And your position is a curve, it looks like that. Okay. Now, if you have another point after this, right, you have to start with this position where you stop. Of course, you don't have to do anything extraordinary here because anyway, the next segment will start from here, right? So this final point position will be the first point position for the next segment. You start over here. And if you look at the velocity, it's 0. So you have to start with 0 velocity. Acceleration, something like maybe -4 or something, right? But you cannot achieve that one. So for the next segment, acceleration will be different. So acceleration discontinuity is there because we cannot control it with cubic polynomials. Is that clear? Any questions, please? All right. Now let's look at cubic splines. Now earlier, you saw the parabolic blends or parabolic trapezoidal splines. Remember? So we have one trajectory using trapezoidal velocity profile and another one, and you combine them together, right? You can create a big trajectory like that. Same thing, same concept here with cubic polynomials, right? So you have a start point, end point, and in between number of via points. So what you do is you take the first 2 points, then the next point, the next point, and so on, and create these trajectories and combine them together. Okay. Now let me show you this example. We already know that when you have a cubic polynomial, you get a S-curve. You get a S-curve for the position, okay, joint angle, right? S-curve. If you have a trapezoidal velocity profile, right, the difference is in the middle of the S-curve, you have a straight line segment, okay? But in cubic polynomials, you don't have that straight line segment. It's a continuously transitioning S-curve, right? So this is the first segment, the first cubic polynomial. This is the second cubic polynomial, right? The cubic polynomial is representing the position. So this is the position cubic polynomial for the first part. This is the position cubic polynomial for the second part. And the first one has 4 coefficients. You know that cubic polynomial has 4 coefficients, A0, A1, A2, A3. And the second cubic polynomial has B1, B2, B3, B4. Now, in the merging process, right, we have 8 coefficients now, right? A0 to A3, B0 to B3. Altogether 8 coefficients. So now you might be thinking, okay, we need 8 equations, right, to solve these 8 parameters, 8 coefficients, right? Yeah. So what are these equations then? For position, this is the cubic polynomial, a0 plus a1t plus a2t square plus a3t to the 3, right? Cubic polynomial for position. Once you differentiate, you get the velocity. Sorry, velocity is over here, and the acceleration is over here, right? This is the first polynomial for the first segment. This is the second polynomial for the second segment, right? And velocity and acceleration are given only for the first polynomial, but for the second polynomial, you can write the same equation using coefficients b0 to b3. Okay, right. Now let's write down the boundary condition. If you look at the first polynomial, the start point is theta 0 at time 0. So first polynomial with time 0, this one with time 0, simply a0. And that is the start point over here, the first equation. And position at the end of the first segment over here is theta v via point. Okay, this is a via point, theta v. So theta v is equal to coming from the first polynomial at time equals capital T, right? This one. And this point is also the first point of the second polynomial. So if you go to the second polynomial and set time equals 0, right, you get the same position, theta v, right? And in that case, from the second polynomial, when time is 0, you are remaining with b0. So it is also equal to b0. All right. So this is the via point. And the final point over here, position, coming from the second equation, when simple t is equal to capital T. So here I assume same t, same time, right? First segment, second segment, same time, capital T, to make life easy at this stage, right? So you can write the third equation for position. Is that clear? The first polynomial at time 0, first polynomial at time t, second polynomial at time 0, second polynomial at time t. Right. Now, velocity. If you look at the velocity equation here, you can write down initial velocity theta 0 dot is equal to a1 from this equation, right? When time equals 0. When time equals capital T, you get theta dot v. And also you can take that from second polynomial, velocity polynomial, it becomes v1. And at the end, the velocity is theta dot f, right? Theta dot f is equal to the velocity expression here when capital T is replaced with, simple T is replaced by capital T, and it's coming from the second polynomial. So coefficient B's, B1, B2, B3, and so on. So likewise, you keep writing these equations, right? For a particular polynomial, it is position, velocity, acceleration. You know the values, you substitute and generate your equations. And if you want to write down acceleration equations here are these equations. Acceleration at time 0 here initially, theta 0 double dot is equal to 2a2 is coming from the acceleration equation here. And at the via point, theta double dot v is given by this equation when simple T is replaced by capital T. And if you want to have the same acceleration for the second half, second segment at time 0, you have to say that this is also equal to 2b2. But I don't think you can do this here because you don't have enough coefficients to satisfy all of these things, as we saw earlier. Right? I'm just writing it over here just to show you if you ever want to make sure the acceleration is also continuous. There's no gap in the middle in acceleration. You need to satisfy this requirement also. And at the end, there is this acceleration, the double dot f coming from the acceleration equation for the second polynomial here, right? 2b2 plus 6b3 t2. So here actually, if you look at this one, I have not assumed T1 and T2 are equal, right? Even though I mentioned we can have T1, T2 separately. Don't need to make them equal. If you want to do analytical simplification, T1 equals T2 equals some T will help. But if you do the numerical implementation, you can put any value for T1 and T2. The only requirement is that you need to know the value of T, right? You can incorporate that. So therefore, T1 and T2 are not equal in general. Now, if we, without trying to solve anything, if you summarize everything what we have done up to now, it's over here on the slide. We have start point, via point, and the end point. Okay, and we have position constraints, boundary conditions, velocity constraints, boundary conditions, acceleration. Sometimes we can consider them as boundary conditions, sometimes not. Let go free, okay? Depending on how many parameters we have, like control parameters. Altogether, we have 8 of them. Now, if I say position, if I want to satisfy the initial or start position, end position, and via point position, right? So yes, we'll take it positive. So we want to make sure the initial position is satisfied, final position is satisfied, via point position is also satisfied. Okay, 3 equations are gone. So 3 parameters are gone. What about velocity? We want to satisfy initial velocity. We want to satisfy the final velocity, 0 or otherwise. Okay, and we want to make sure at the middle point velocities are satisfied, right? End velocity of the first trajectory, first polynomial is equal to the initial velocity of the second trajectory, right? They should be matched together. In fact, this equation, you can see it over here, right? The position merging, and this is velocity merging, right? Now, 3 parameters are gone for velocities. Now, 3 and 3 is 6. We are remaining with only 2. We can select any 2 of these. Shall we satisfy the initial acceleration and the final acceleration? If you say yes, we can do that. Then that's all what we can do. And at the via point, in the middle point, you cannot satisfy the acceleration. So the acceleration with which the first cubic polynomial ends is not equal to the acceleration with which the second polynomial starts. So therefore, there's a discontinuity at the via point in joint acceleration. This is the maximum you could do with a cubic polynomial. Okay, so you can see it over here, A0, A1, A2, A3, B0, B1, B2, B3, 8 coefficients and 8 equations. You cannot satisfy all of the equations, not all, but many of them, right? Now, once you do that, you will see something like this. This is the first cubic polynomial, right? The second one, the third one, fourth one, fifth one, like that, it goes on and on and on. You can actually merge any number of these cubic polynomials because at the end, right, at the end, the positions, velocities, and accelerations are merged together. As we saw earlier in this table, start and end point, we satisfy the position, velocity, and acceleration. What we do not satisfy is the acceleration, continuity at the via point, right? Only that. So start point and end point. So if you look at the start point of the next cubic polynomial is equal to the end point of the first polynomial, the polynomial before that. So you can satisfy all of these things in the table. Then you have smooth motion continuously, except at this point, midpoints, where the acceleration is not continuous. So I do not expect to generate any assignment out of this. But if you can take this as part of your second assignment, so much the better, because now I'm going to give you an extension. Think about some of these algorithms, right? To code your trajectory using either, I don't recommend you do uniform trajectory planning, uniform velocity, but if you can try velocity, trapezoidal velocity profile or triangular velocity profile, or maybe something like this, right? It would be really interesting to see. Now, what if you want to satisfy acceleration constraints that you were unable to do that? The planning algorithms we discussed so far. If you want to satisfy or control your not only acceleration, but maybe jerk as well. What do you think? What do you think we should do if you want to control acceleration and beyond, jerk, etc.? What do you suggest? The condition is this. You can satisfy the boundary conditions up to the number of coefficients in your polynomial, right? You know that. If it is cubic, 4 parameters, 4 coefficients, right? And you can satisfy that number of constraints. Now, when I say constraints, these are the boundary conditions: position, velocity, acceleration, jerk of the endpoints. Now, if you want to control acceleration and jerk, your set of equations go beyond what we earlier had. Remember, in the position, velocity, acceleration case, right, we had 6 equations. One polynomial, 6 equations. But the one polynomial has only 4 parameters. You can satisfy only 4, not 6. Now, if you want to actually control all 6, initial position, velocity, acceleration, final position, velocity, acceleration, 6, then you need to have what? 5th order, right? 5th order polynomial. Now, if you have a 5th order polynomial, you have 1, 2, 3, 4, 5, 6 coefficients. There you are. You have 6 coefficients, and you can use this one to satisfy 6 constraints. So 2 positions, 2 velocities, 2 accelerations. You are done. Okay? So you need to go for higher order polynomials if you want to satisfy more and more boundary conditions. All right. So that's the last slide. We have little time for discussion. Any questions, please? Anything that you don't understand? Anyway, here I can explain a little bit about the graphs you see here, right? This is the 5th order polynomial, And you can see the position. It's like a curve again, right? Goes like that. And this is the velocity. It's similar to the previous one also. You can see that. This one, right? It's parabolic velocity profile. But here is more like Gaussian shape, right? And then acceleration looks like this. You can see 0 and 0. That's great, right? You can start with some 0 acceleration and that 0 acceleration. So much the better. You can satisfy all these things. And you can even go for the third derivative, jerk. It'll look like this. So more and more constraints can be satisfied with the because we have high number of coefficients now, right? All right. Any questions, please? Right. If there are no questions, let's wind up the session today. And please make sure you submit your assignments, and I'll give you an extension 1 week. And I'll see you next week. Have a good evening.
Good evening, sir.
Thank you.